Okay, hello everyone. Good to see so many people attending the talk at the end of day one. I'm very excited to be here presenting you this research on how we attack the Galaxy A family of Samsung devices. So today on stage with you, you have Maxime, who is also the main contributor of this research, and me, Damiano. But we also need to thank Gabrielle and Raphael for their contribution and helped us make this possible. So this research started last year at Quarks Lab, and it is kind of a result of a previous research that we did on a modern data encryption in Android. Essentially, what we wanted to do in this previous research was understand how modern Android encrypts storage, so data at rest. So we started from a phone that was vulnerable to a known boot ROM bug, and we used it to kind of dissect how the various components were interacting with each other, how the user credentials were used to derive the keys that were needed to encrypt and then decrypt the data. So this was an interesting research, and from there on, we thought, yeah, let's maybe make it more real. Let's try to do some actual vulnerability research. So today we're presenting a chain of bugs that, starting from the USB stack, can lead to full compromise of this family of devices. So we worked mostly on devices like this one. So it's this Galaxy A family. It's kind of in the low tier of Samsung devices, pretty cheap, I would say. These devices usually run a MediaTek SoC. And there is this combination of MediaTek and Samsung code that is running on the phone. As a trusted OS, we have Tigris, and yeah, so with these phones, some of these phones are also vulnerable to this known vulnerability that you can use with a tool called MTK client to bypass a secure boot. So we did not use the vulnerability in our chain, but it definitely helped us while we were working on this to make debugging easier. So to make sure we are all on the same page, we're going to give a few elements of context. So starting with the MediaTek secure boot process, you can see on this slide how the few components interact with each other. We start from the boot ROM that runs in the secure world. If you're familiar with the Android ecosystem a little bit and ARM chips, you know there is this division between the normal world where the most of the software runs, and then this secure world that is meant to be isolated and protected, right? So the boot ROM spawns a second bootloader that is called preloader in MediaTek, and this preloader is then giving execution to three different components. We have here on top the secure monitor that is inspired from the ARM trusted firmware. This is going to stay in execution and for even after boot, and is the most privileged component that we have in the whole OS. Then we have the Tigris trusted execution OS. This has both a kernel and a userland with the trusted applications. And then we have little kernel that is the main bootloader for the Android OS that will in turn boot Android both in kernel and userland. So we start our presentation from little kernel, but before diving into what it is, how it looks like, we wanted to introduce the concept of partitions. So basically partitions are the different components that build up an update, or basically these are the things that you can flash when you want to recover your phone and these kind of things. So there's a few. We're not naming them all because a slide wouldn't be enough for sure. But we want to, for example, give the boot image as an example. This contains the kernel and the RAM disk. Then we have the VB meta partition will be useful later on for verified boot. And we have the super partition. There is this dynamic partition, a bit of a special case because dynamic partitions are implemented in userland. So a bootloader will not use a dynamic partition, but the super contains the Android framework, the vendor binaries, and this will be useful as we move on. So we mentioned little kernel. This is an open source project that is very often used as a bootloader in the Android ecosystem. It allows to boot Android normally, but also supports some alternative modes to recover the system and flash do things that to rescue the system when something happens, for example. And it implements AVB, Android Verified Boot, which is the framework behind the verification of Android images, also making sure that there is no rollback possible. So Samsung took little kernel and added some additional features. We can note, for example, the support for the ODing recovery protocol, which is also used to flash partitions and rescue the device in case something happened or if you want to update. There is the Knox security bit as part of the Knox suite in Samsung phones. Now, this bit is essentially just a way to void warranty when a bootloader is unlocked. So maybe security more on the side of the vendor than of the user. And then we have, among other things, many of which we probably don't know, a JPEG parser and a renderer, which is used to basically create messages like the ones you see in this slide. So when something is broken, that you have this nice image that tells you what happened. So LK by Samsung is closed source, but obviously, since you have the open source version, reverse engineering is not too complicated. So I'm going to hand it over to Max so we can get started with the fun stuff.
Thank you. So we actually, we actually started to look into this JPEG parser. It quickly raised our interest, mainly because the JPEGs are placed into a tar archive that is present in a partition called up param. And this archive is signed, but it's not verified at boot. It's not checked at boot. So anyone capable of writing something on the internal memory can, in the end, modify these JPEGs, which is quite interesting for an attacker like us, because, as you know, parsing JPEG can be a difficult task. Here we cite logo fail, so research by binary. They presented many vulnerabilities on image parsers in various boot chains. So it's a lot of failure happening in these JPEG parsers. So the question for us is how are these JPEGs loaded in little kernel? So this is the code responsible for that. And you see, first, there will be an allocation of a constant size allocation for our buffer. Then this function we call the read JPEG file. So the name is the one we gave through reverse engineering, so it's probably not the official one. But you get the idea. This function will actually read the JPEG from the tar archive using a file name provided in argument, and it will write the content into the JPEG buffer previously allocated. And finally, you have this, this function that is called to parse and render the JPEG on screen. So some of you may wonder why do we have this third argument, 0 as a third argument in this function. And actually, it's supposed to be a maximum size. So whenever the system reads the file from the tar file, it will first check the size. And if it's bigger than the size provided, it will trigger an error. Unless the size is 0. Which is the case here. So when it happens, it will simply read the file and fill the buffer as it will fit, which is not the case, which is not necessarily the case. So we have here first vulnerability. It was pretty quick, heap overflow. And is it exploitable? So to answer that question, we need to understand how the heap algorithm works in little kernel. And it is actually called mini heap. It relies on a doubly linked list. You see on the right the format of the header, so you have a pointer pointing to the previous chunk, then another one pointing to the next chunk, followed by a size, and then followed by the content of the chunk. So all the chunks are following each other in the same unique memory pool, which means that when an overflow happens, you may overwrite the metadata of the next chunk. And there are various ways to exploit this type of bugs. We could, for example, overwrite interesting data, such as function pointers coming after the chunk containing the JPEGs. But in our case, there is nothing really interesting. So we found a way to turn an overflow into an arbitrary write. And this is because when an allocation happens, a chunk is removed from the free list. So by controlling the prev and next pointers of the current chunk that is being allocated or being dereferenced by the system in order to access the next and previous chunk and make them point to each other. So by controlling these pointers, so the header of one chunk, it can lead to a write-what-where primitive, with the only constraint that both values must be writable addresses. Now, a few words about mitigations in little kernel. So as you can see, there are not many mitigations. No ASLR, no canaries, no bound checks in the heap algorithm. And most importantly, the heap is executable, which is very convenient for us. So the exploit strategy is very simple. We will use the write-what-where primitive to overwrite a pointer somewhere where the code will jump to. And in this case, we use the return address in the stack. And we will make it point to a shellcode inside our JPEG buffer. To give you an example, this is the state of the heap when after the allocation of the JPEG buffer. So then we will read the JPEG and fill the buffer until we overflow the next free chunk. And we will replace its content. We will create a fake chunk where the next pointer points to the return address and the pref pointer points to the shellcode, so that when the system will remove it from the free list, it will dereference next, so access and replace the return address with the pref pointer. And after the function returns, as you guess, we have a code execution. So this is the theory, and to validate that we implemented an emulator using Unicorn. I'm sure all of you are familiar with Unicorn. It's simple, I mean, it's a CPU emulator, very simple to use, very straightforward, and we actually implemented our exploit here. But the problem is that even if it works on the emulator, it does not work on the real device. So what can go wrong? The first thing is that the heap and the stack are different in both environments. So to overcome this, we actually used the vulnerability, the known vulnerability Damiano mentioned, to dump the heap and the stack, so we had to patch little kernel to do so, but it's not impossible. There is another way to do this, is to reproduce the exact same succession of free and malloc, because we don't really care about the content of the allocations. In this case, we just care about allocations and the order of, I mean, in which free and malloc is being called. And this is possible because here we are talking about a bootloader with no ASLR and so on. So it's quite deterministic, and the state of the heap is going to be the same every boot. The other problem we had is that the heap algorithm will write something at the address shellcode +4, and this is because the routine used to remove the chunk from the free list, so we will access the system will access the previous chunk to overwrite the next pointer. But it's very simple to overwrite. We just need to skip the next instruction. So if you are familiar with the ARM assembly, it gives something like that. And the last problem we had is that the heap is broken after exploitation, because we changed the free list. So we need to restore it so that the next allocation works and does not crash the device. So to sum up on this vulnerability, you have the CVE number. It leads to a code execution in little kernel, and it's persistent. It will survive reboots and factory resets because the apparent partition containing the JPEGs is never wiped with these actions. And it will give full control over little kernel, which runs in normal world EL1. And since little kernel will load Android with a little bit of work, we can disable the checks and take control of the Android system. And yeah, finally, this vulnerability impacts many Samsung devices based on MediaTek socks. Actually, all those we look into, which includes also devices that has the newest MediaTek system on chips fixing the boot ROM vulnerability we mentioned before. So the problem we have now is how can we need a way to flash this apparent partition, the one containing the JPEG, and not rely on already having privileges. So the way we did it is to look first at the Odin recovery protocol that is implemented by Samsung in little kernel. And it actually allows to flash partitions over USB. So there is an official client that is closed source, but there is also an open source one that is very handy called AIMDAL, and it's the one that we used in most of our proof of concepts. So internally, Odin will use two internal structures to flash the partitions. First, images needs to be authenticated, so they must contain a signature, as you see on this code snippet. And so there are two internal structures. First of all, the partition information table that we will call the PIT, and a global structure that indicates which partition to authenticate. So the PIT is retrieved from an hard-coded address in the eMMC, and it indicates where are the partitions, what are the size of the partitions. You see here an example of an entry in a human-readable form. So you have the name, the size, and so on. And a partition that is not present in the PIT cannot be flashed through Odin. Another interesting thing is that we can update, the PIT can be updated, but it requires a signed image, as you can imagine. Now, regarding the image authentication, we have this global array, and an image that is not present in this array will not be authenticated. There are some exceptions, but we will not cover that today. So overall, if you compare the PIT partitions that we can flash and this global array, the ones that are authenticated, it gives you a list of partitions that can be flashed without authentication. One thing we can note first is that the up-param partition containing the JPEG is authenticated. So the signature that was inside this partition, if you wondered why it was there and not used at boot, it's because it is used by Odin before flashing it, it's going to be authenticated. So among those that we can flash, there are PGPT and SGPT that are particularly interesting. GPT standing for GUID partition table. So these two partitions point to the two header, primary and secondary header of the GPT table. And it's similar to the PIT. For those who don't know what is GPT, it describes the partition. You will find information such as the partition name, sizes, and so on. So it's the fact that we can flash this partition without authentication is quite a powerful primitive, since we can use that to reshape completely the partition layout of the system. So you might wonder why we have this GPT and PIT at the same time, since they are doing the exact same thing. Actually, the PIT is used by Samsung features, such as Odin or the JPEG loader, and the GPT table is used the rest of the time, such as loading Android images. So the up-param partition we are particularly interested in too is retrieved using the PIT. So we cannot simply change the GPT table to mess with it. But there are other interesting things that can be changed, such as the PIT table. So let's first take a look at how the PIT is loaded. So as I explained before, it is present by default at a fixed address that you see here, but it is implemented that way in the code. So the code will first see if there is a PIT partition, and if it's the case, it will load it from there and not from the default location. By default, there is no such partition in the devices we looked into, but still it exists. And the thing that is particularly interesting for us is that these two functions actually use GPT table, and we can change this GPT table. So we could flash a PGPT partition, add a PIT entry, and at next boot, the system will load the new PIT from this entry instead of the default one. So we came up with the following strategy. You see here the flash memory. We have the PIT and the GPT that pointing to more or less to the same partitions. And if you recall, there is this MD5 HDR partition that is one of those we can flash without authentication, and it's actually not used, so we can overwrite it. And we put here a new up-param partition containing the JPEGs, the malicious JPEGs. Then we do the same with the VB meta vendor partition, which is also flashable and seems to be empty. And here we will place a new PIT file. So it's exactly the same as the default one, except that we will rename the MD5 HDR partition into up-param. And finally, we will change in the GPT table the name of VB meta vendor, we'll rename it PIT, so that at next boot, the new PIT is taken into account by the system, and the new up-param partition will be read instead of the old one. And it actually works. If you see the dodge here, it means that the exploit worked. But there is still a problem. Android won't boot without the VB meta vendor partition, even though it's, we can put anything inside, but still the system will complain if it's not present in the GPT table. So to overcome that, we simply rename another partition that seems to be unused into VB meta vendor, and thanks to that, it actually will boot without any issue. So before we get to the demo, to sum up on this vulnerability, so we can bypass the authentication in Odin. We can flash anything in the eMMC, including the upper partition. And this vulnerability impacts most devices, most Samsung devices based on MediaTek SOCs, but we discovered that some Samsung devices based on Qualcomm SOCs are also impacted, since you can flash. They have GPT table that you can flash without authentication as well, even though the exploitation will probably be different. And yeah, a few words about post-exploitation. Remember that our ultimate goal is to take control over Android. So there are these, there is this feature called the Android Verified Boot that will verify the Android partitions, make sure they are the original ones. And the way we will take control over Android is that we will simply modify these partitions. So we had to implement a little routine in our shell code to patch little kernel, the code in the RAM. And it's actually pretty easy to do because the memory is already writable. So no need to play with the MMU. You see here an example of a check that is performed. There is a hash that is then compared to a stored value, so it's pretty simple to patch it. You simply nope the if or make sure the memcompare is returning true every time. Time for a demo. We will try the live demo. Hopefully it's going to work. So first, well, no. Okay. All right, let me just show something. So I just want to show you here I'm connected to the device with ADB. SU does not work because there is no SU binary, all right? It's the normal system we have here. Let me just prepare the command line, yeah. So I will shut down the device. Note that a device like this one, most Samsung devices can be shut down without authentication. So you just long press all the buttons and it should turn off. Then I will start the device in the Odin mode. And now we run the exploit. So well, it's pretty fast. The exploit is flashing all the partitions I mentioned. There is a little trick here because in order to flash the Android partition that we modified, I will not cover it today, but yeah, this is what is happening right now. And you see Dodge showing up. It means that it worked. So now we have to wait for the device to boot, and it's actually quite long. Sorry for that. Can ask Samsung to improve a bit this boot time.
They're trusting us because we are not really root yet.
You can see that. It's even longer than usual. All right. So IDB shell again. This time SU should grant me root privileges, as you can see.
Thanks to Samsung, we did 2 applauses instead of 1.
Okay. All right. To conclude on this first part of the presentation, so we have a chain of 2 vulnerabilities. That leads to code execution in little kernel with persistency. It impacts many Samsung devices. You can trigger it through USB thanks to the Odin bug. And it gives full control over the normal world, so over Android. But we still don't have access to some of the secrets that remain hidden in the secure world. So for this part, I will let Damiano continue.
Thanks. So yeah, actually the presentation could be already over, and maybe we could get a coffee or something before the next talk. But I mean, we are fully in control of what is at the bottom of the schema, the normal world, including the bootloader and the Android OS, both in kernel and userland. But there is this secure word that is still untouched, and so what we wanted to do next is try to challenge this secure part of this word. And to do so, we started from the ARM trusted firmware, so the secure monitor that is running at EL3. This is a component that is critical for the way the system works, because it is the one that is letting the secure word and non-secure word communicate with each other. So say that at some point the Android system wants to perform some operation that needs to happen in the secure world. You can think of user authentication, for example. When you unlock your phone, there is a call that goes to the gatekeeper trusted application. Or when you use a key, often you end up using the key master trusted application. So there is a sequence of operations on the Android side that will at some point send an ioctl to the kernel that in turn will send an SMC. And this SMC is a special instruction for in ARM chips that triggers an exception. This exception will be handled by the secure monitor. Now at that point, the monitor decides what to do based on the ID of the SMC. It can either process the request itself, or it can forward it all the way to the trusted application that needs to pick it up. So this component, as I said, this is a very, very critical one, and given what we have built so far, we also have a way to reach it. So through the normal world and SMCs, you can end up talking to this ATF. So it's a very interesting attack surface, this one of the SMC handlers that we wanted to explore. But SMC handlers are very simple. What they do is usually interacting with some hardware, maybe memory mapped registers, but it's not really the kind of situation where fuzzing helps a lot. Again, because much of this code is very low level, you have to build a lot of hooks, and instead we decided to focus on simple static analysis, and as we will see, it's already effective enough. So we previously introduced the OS, the trusted OS, that's Tigris. It's been designed by Samsung, and its components are spread around different images. So we have TEE verified for ATF, the kernel, and the user boot library. Then the file system is in another partition, TZAR, maybe trust on archive, something like that. And then the super image contains, in the vendor side, the proprietary binaries that are the trusted applications. But we will not talk a lot about Tigris. There are excellent references online, and also on this stage a few years ago, Riscure did very good presentations on Tigris. So if you're curious, there's a lot on that already. What we want to go is, what we want to show a bit is this ATF. So it will appear in the partition more or less like you see on this slide. So we have like a 0x200 bytes of header. Then the code itself, you can spot the MTK TEE sort of magic at the beginning. And then there is a footer with a signature. And once you load this in your favorite disassembler, what you want to look for is the SMC handlers, as we said. And they can be reached through two different routes, we can say. One is from the secure world, and one is from the kernel, right? So either the secure world wants to talk with the normal world, or the other way around. So we focus on the kernel surface. What I want to draw your attention on is these parameters. So the SMC IDs and the arguments are really just the registers that are set when sending an SMC instruction. So SMC handlers, we start having a look at them, and we immediately found this one that looks pretty interesting. So you see from this ID, this SMC seems to provide a feature to read something from a global array. But the thing is, this argument is coming from the SMC request, right? And it's fully controlled by the attacker and never really checked. So basically, this to me looks like an arbitrary read, that has been wrapped into an SMC handler. So yeah, reachable from the kernel. Just need to send an SMC with that specific ID and an address, maybe applying the offsets to make sure that you get the address that you want. So this allows to leak 4 bytes of memory from the ATF address space, which is nice and obviously is not supposed to happen, I guess. But there is not that much to leak inside the ATF. If we think about the interesting secrets that we may want to leak, they are usually associated with the trusted applications. So it could be nice if we could also, load the trusted applications somehow and access their memory. And well, it turns out that there is a way to do that. With this other SMC, you can end up calling SPM actions. Now, once again, this is a name that we gave through reversing, so we don't know if this is the real name, but we seem to be quite sure that it has to do with power management. And what this function ends up doing is taking the arguments as usual and almost immediately calling a memory map without checking the address in any way. So essentially what happens here is that you can ask to map a physical address to the same virtual address so that it is then accessible by the ATF. So another, I guess, SMC handler that is doing something that is not supposed to, also reachable from the kernel. We can memory map any address, only up to 8 megabytes though, because we can't unmap. So if we map too much, we end up crashing and and having an unstable system. But this is already quite a bit of data that we can map. So if we chain the 2 bugs together, the one that I've just shown and this one, it means that we can memory map anything in the address space of ATF and then leak it with the other bug. With an example that we have already shown in the past, and we think it's a pretty useful one to show the impact of a similar attack, is attacking keystore keys. Now, keystore is one of the services that relies on the TEE the most in the Android system. Just to give you a very short introduction, keys in the Android ecosystem, in the Android world, are usually generated and stored as key blobs. So essentially, key blobs can be stored inside the file system, but the key material inside is encrypted and can only be used inside the environment it belongs to. So the idea is that you have different protection levels, and when you have to use the key, you will send the key encrypted to the protection level of choice, to the component that runs in that protection level that will use it. So, for example, imagine at some point the normal world wants to use a specific key to sign something or to encrypt, decrypt, whatever. It will send a begin operation message to the component of choice. It can be keymaster TA if we are talking about a TEE level, or the trusted chip for Strongbox. And this component will extract the key, use it, and then send the result back without revealing the key. So what we need to know now is where to leak, where we can, what addresses we can map in memory so that we can try to leak them afterwards. And investigating the logs that we have available. These specific logs that you see here are LK logs, little kernel, and the addresses are physical. We see that there is an interesting range that says TEE reserved. So we were like, let's try to investigate that, and indeed, that's the place where TA seem to be loaded in memory. We can find many of the strings that belong, for example, to the keymaster trusted application. And just as a reminder, the binary is available on the file system, so one can very easily have a look at it. And yeah, we do find the strings of this TA in memory. So at this point, the POC becomes very simple. We want to import a key into keystore. Then we want to use it, for example, with an encryption, but stop the execution right after begin operation is called. So at that point in time, the key will be loaded in memory in the trusted OS, and that way we can leak it. So this Java code allows to import a key full of A's in this case. It can be used in an application, for example. And what will happen, going back to the schema before, is that the app will trigger the operation. And we want to hook, for example, with Frida, right the keystore service after the begin operation has been sent. So the result when we leak memory is something like this. We can see the key from the leak, but I mean, that is not that exciting, right? And we have seen better things on this stage. We already knew about that key. So to improve it further, we could import or even just use any key, right? Proceed as I just did, but try all the possible combinations of the consecutive keys, the consecutive sequences of bytes to see when we can actually decrypt something successfully. So now it's time for our second demo, and yeah.
Okay.
Okay, so we are opening now. This time, no need for the camera because the device is already on. We have a few things that help us with the demo. So on the different terminal windows, we will first of all launch, spawn the Frida server so that we can hook the daemon as the service as we've shown, and then we have an app that is meant to help us. That will basically just log on the Android logs, the ciphertext, and IV, just to make it easier. Then a script that is hooking with freedom, and here I'm gonna type some message, encrypt it. Did I encrypt it? Yes?
No, it's okay.
Okay.
It's taking a bit of time.
Okay, so what is happening now is that our script is also launching the exploit. We are not showing it, but basically we need to have a kernel module that is sending the SMC calls. And yeah, so we will leak a bunch of memory in the addresses that we have seen before, and then take them from the Android file system to do the tests. Did I? Because we don't see the IV, right?
Yeah.
So maybe I haven't pressed encrypt, or what?
Oh man, that's the wrong command. Okay, let me try again.
No, QB is meant to match the logs.
Okay. Yeah, we had it.
Okay. So we just take the ciphertext and the IV just because it's handy to take them from the logs. And we do some base 64 magic to make our script happy, I guess. No pressure.
Okay.
Python.
Too much pressure.
So yeah, this will try all the possible combinations from the leaked memory that we have, and hopefully it's going to find the key. It is the same in this case, and the ciphertext.
That's okay.
Yep, good. So yeah, we could also avoid using Frida. We did it because it's handier here, but we can also just use the Tigris userland libraries directly. But anyway, the result is going to be the same. So to conclude, we presented a total of 4 vulnerabilities. The first one allowed us to bypass the authentication of an image in Odin. Then we can flash a malformed JPEG that will get us code execution in little kernel. so that we can own the normal world, both in kernel and userland. And then with other two vulnerabilities, we can have arbitrary memory leaks from the secure world, which essentially means that the device is more or less fully compromised. What we would like to reflect on is that, yes, we targeted low-end Samsung devices. So not the ones that are usually being targeted by the security community, but still we found pretty simple bugs and basically no mitigation, right? Finding an executable heap or this kind of very simple bugs in ATF was very surprising and a bit sad, I must admit. But anyway, now all vulnerabilities are fixed and the talk is over. We're happy to take any question.
Could you use this to leak Android key attestation keys as well?
Sorry, do you mind saying it again?
Could you use this to leak Android key attestation keys? No?
So the question is, can we use this type of vulnerabilities to, I don't know, mess with the key attestation?
Yeah.
I think there is a secret that is derived inside the secure world.
Yeah.
I'm not super familiar with the key attestation, but I think it's something like this.
Okay. Yeah, cool, cheers.
So yeah, if there is a secret, for sure we can leak it. Unless it's stored in another hardware, in that case, yeah, we need other vulnerabilities for that.
Thanks. That was very impressive and interesting. It seems like you found the vulnerabilities quite quickly in both cases, so I'm wondering if you kept searching for more, or is it likely to assume that there are more simple vulnerabilities of this kind in those targets?
Well, I think the question is kind of giving the answer already. So, no, but I mean, yes, it is true. It didn't take that much to find, for example, the heap overflow. But the exploitation was not as easy. For example, like if we didn't have that already existing vulnerability, it would have been even harder, right? And yeah, in these situations, it is true that you have no protections. But I guess what makes it harder is also having no debugging, no introspection, nothing, right? So you just see, I don't know, blue screen like in Windows, like you have seen before. And you don't really know what's going on. So, yeah.
No, I was in no way implying it was easy. I was just curious how likely it is to get more bugs out of them.
Yeah. No, but it was easy.
Thank you for the talk. You said that they patched the vulnerabilities, like the GPT, the fact that you can bypass, you change the GPT and the heap overflow. How long did it take them to patch, and did you check the patch to see if it was bypassable and stuff?
So no, we didn't check the patch. Not all of them. I think for the GPT issue, it was pretty fast, like 1 month, maybe 2. For the others, it took a bit more time, like 4 or 5, don't recall precisely. And also MediaTek, there is one bug that we reported to MediaTek, and they were super reactive. They fixed it in a couple of weeks.
Thank you.
Okay. Thank you, everyone.
Thank you.